Hi, my name is Nathan Reidinger. I'm a PhD student at the University of Maryland. Today, I'm thrilled to be able to present to you some work I did with my advisor, Michelle, on improving the state of art in blocking a particular type of tracking known as canvas fingerprinting with our tool, MLCB. Of the many types of tracking that occur online, one of them comes from HTML5's canvas element. To couch this concept in realistic terms, imagine that you visited the website lenscrafters.com. This is what that website looked like in June of 2021. What you don't see here are canvas images. Many of the images you see are files that are served to you rather than images drawn to the canvas. That's not to say this page has no canvas drawings. To find the canvas images that are being drawn by this page, you'd have to dig into the website's source code. This is because canvas fingerprinting is a mechanism that can be done without any user awareness or user consent. It's surreptitious in this way. If you did dig into the website source code, you'd find this piece of JavaScript code. This code's purpose is actually to draw the following image. This image is a canvas fingerprint. So the website told my device to draw the image. The image turns out to be one that is bespoke to my device's particular hardware and software characteristics. And the site can therefore track me by using this program, and especially that final call there, toData URL, noted on the last line. Canvas fingerprinting originates from a 2012 academic paper explaining how you could draw a particular style of image to the canvas and it would provide you with a pretty good fingerprint. The fingerprint would be consistent, it really pulls out the uniqueness between devices, it fits well with existing fingerprints, it's transparent to the user, and it's readily available. Looking at the code used on the LensCrafters website allows us to get a pretty good sense for how canvas fingerprinting works. What a canvas fingerprinting program aims to do is draw something to the canvas that uses letters, colors, and shapes, and tries to create a lot of variation. This program on the left draws the image on the right. The two versions are from two different computers. To give you a sense of the variations here, we can look at variable C. This is actually something known as a pangram. It uses every letter in the English language. Another notable feature is the call to toData URL that I mentioned before. This function returns a base64 encoded version of the drawing, which can then be compared to other strings to identify similarity or dissimilarity. So the two images on the right look very similar, and I told you that they were drawn by two different computers using that same program. If I showed you them back to back with the naked eye, you'd have a hard time distinguishing them. But if I showed you the base64 encoded string as a result of that toData URL call, it's very easy to see that they start to be distinguishable on line 3 and moving forward. The Tor project said that canvas fingerprinting, following plugins and plugin provided information, was the #1 threat that browsers face in terms of a privacy loss. Part of the reason the canvas is so tricky in terms of it being a tracking vector is that it's a dual-use technology. The same mechanism that makes tracking possible also makes useful functionality possible. So similar to how if your computer is served text that's dynamically rendered on your screen versus being served an image of that same text, dynamically rendering the text is going to look better than the image. And this is what the canvas allows. It allows you to have images that look good because they use your computer's hardware and software characteristics. In that light, this paper's main aim is to try and block only those canvas actions that are geared toward tracking. This talk has 3 parts. In part 1, the background, I'll discuss how canvas fingerprinting is currently blocked. Part 2 will be our approach to blocking tracking-focused canvas actions. Part 3, I'll discuss our results and how our approach compares to the state of the art. So let's get started with part 1, the background. Identifying and blocking canvas fingerprinting is not a new problem. Several other works have made attempts at blocking this tracking vector. One of the initial ways to block this type of tracking works by modifying all of the images that are drawn to the canvas. So here we're injecting noise into these canvas images, and that creates broken consistency. So the same user visits the same website multiple times, but draws a different canvas image, and that thwarts the classification of that user. This is actually a fairly safe method, but has limits to functionality because we're affecting the canvas images that we're drawing. A second option is to disable canvas images by default and ask the user for permission to render. Again, this is quite safe. It makes the default setting a fairly high standard of protection. The downside here is that it requires the user's knowledge and attention on whether to allow a certain canvas action. A third way to approach this problem is to use a block list. So here, in the naive sense, we can use something like a hard-coded string match. So think the disconnect list, where we're using a regex match on a particular URL, and if it's a match, we're going to block that resource. In a more nuanced sense, you can look for a certain mixture of attributes that are associated with what you're trying to block. There's a very influential paper out of 2016 that discussed how certain height, color, and specific API calls were associated with canvas fingerprinting. So if we identify these attributes, we can then block the resulting actions. These approaches are fairly nimble because they don't block things on a very large scope, but they're not as flexible as we might hope because they're taken when we have a snapshot of what the canvas images used for fingerprinting look like. And those may change over time, and so you have to update the heuristic or the hard-coded lists. To add some flexibility, another line of work uses machine learning models to make that block-no-block decision. The linchpin for this line of work really concerns the ground truth because we're using supervised learning in our machine learning. And the work thus far in the 2017 paper has used ground truth of manually inspecting the programs that are used for fingerprinting, which can be quite laborious in the end. The work out of 2021 uses the heuristic as ground truth and then builds upon it in an iterative fashion. But we're still using that heuristic. So what our paper does is tries to improve the ground truth of the process of gaining ground truth. And we do this by using a fairly intuitive method. If I showed you these two images on the right, it'd be fairly easy to tell which one makes sense for a website, the one on the top, and which one doesn't, the one on the bottom. And we can use that easy human judgment to create our ground truth. What we're actually going to do is take this one step further. So we have this easy labeling process, but we'd like a data source that is 1, not easy for an attacker to change, and 2, more stable over time. Images can be changed fairly easily, but the programs used to draw those images that have certain API calls and certain structure associated with them are difficult to change. Using images for labeling and text as a data source additionally allows us to label hundreds of programs with a single image. And this turned out to be true because what we found was that a lot of these programs that are used for fingerprinting are cloned across the web. Moreover, when we use text, we're allowed to use tools like JSNice. JSNice deobfuscates JavaScript text by using machine learning to predict names of identifiers and annotations of variables. So essentially, we're able to pull natural language meaning out of otherwise minified or obfuscated JavaScript text. Let's turn to the approach that we use to build our classifiers. The end goal here is to have enough data to be able to train a machine learning classifier. So we need to gather a lot of canvas images from the web. To get these images, we built a custom Google Chrome extension that grabbed data about the canvas as it was used by websites. We targeted roughly 500,000 websites listed on Alexa top sites for the initial scrape, and this initial scrape occurred in 2018. Of those roughly 500,000 websites, we successfully grabbed canvas drawing data from about 200,000 of them. We looked at all of the images returned by this scrape and were able to create our set of ground truth. Our machine learning models were then able to train on this data from the initial scrape. We had about 84,000 programs and 3,500 images, and these are the distinct counts in each of those respective categories. To assess how well our models would behave in the real world, we rescraped the web in 2020. We pulled down 408 programs and 181 canvas images, and then used this new data to assess our model's performance. Before diving into the results of that performance, because we scraped nearly 500,000 websites, we were able to assess the state of the canvas on the web. I'll next discuss a few of our measurement insights. Firstly, the canvas is not a tool used exclusively by fingerprinters. In fact, the top 5 most common images, listed in occurrence from most to least, left to right, are all emojis. This non-majority use case fact becomes more obvious when you look at this information in terms of the Alexa rank. So here we have intervals of Alexa rank, the 1 to 100 category, 100 to 1000, and 1000 to 10,000 listed along the bottom. On the left, we can see the percentage of websites that fall into that interval that are associated with either using ToData URL in gray, or using ToData URL for a fingerprinting purpose in blue. What this chart also allows us to see is that when we compare this result with prior work, we find that there's a trend that's rising. So in 2014, previous work found that 5% of websites that were in this interval, the 1K to 10K range, used ToData URL for a fingerprinting purpose. In 2016, this number was updated to just 7%, and our original scrape in 2018 showed that 11% of these websites were using ToData URL for fingerprinting. So even though canvas fingerprinting is a minority use case here, its use is rising. Secondly, when looking at the programs that drew canvas fingerprints, we find that there's quite a lot of overlap between programs. Another way of saying this is that code cloning is the norm here. In fact, if you did a comparison of all fingerprinting programs, so pairwise, you'd find that the mean Jacquard similarity score, in other words, a way of measuring the overlap here, is 40%. Finally, like other research, we found that websites that were monetized by advertising were most likely to engage in use of the canvas for fingerprinting. News consistently comes up as the #1 category here of websites that engage in canvas fingerprinting for tracking, but we also found that cooking recipe websites and websites related to arts and entertainment commonly employ this tracking technique. Now let's turn to the performance of MLCB, how our models do when compared to the state of the art. As background, we dug deep into the performance of assessing our models on many different fronts. The first of those is our original scrape data. So here we have 2018 data, which is images and text. The second is our test suite data. We also have images and text, but this is from 2020. Finally, in order to assess how our models would fare against an adversary who obfuscates website source code in an attempt to try and trick our classifiers, we took text from the test suite and we ran it through the JavaScript obfuscator tool. So we're trying to create obfuscated JavaScript as an adversary might and see how our models do with this type of data. Here's some of our performance metrics. A few basic points to cover here. The F1 score is a harmonic mean between the precision and the recall. The 3 models listed, they're all text-based, and the text that they're using as data has been transformed with JSNice. Additionally, these results are generated using stratified k-fold cross-validation. You can learn more about this and other details in our paper, but at a high level, the 3 different data sets that we're looking at here and the scores that we have essentially assess how well do these models do with fresh, contemporaneous data, how well do they do over time with the drift between 2018 and 2020, and how would they do in the adversarial setting. I'll now drill down on a few high-level points about these results. For one, our models all work well with contemporaneous data, the data that comes from the original scrape. Additionally, the best model here performs well overall, with F1 scores at or above 80% across all 3 data sets. Secondly, our classifiers work fairly well even with the 2-year drift that occurred between our original scrape and the test suite scrape. We can also see here how the CNN would do. Although it competed with the test-based models initially, as we can see in the original scrape data, the red dot showing the CNN is above 85%, it seems fairly sensitive to the new data that was found in the test suite. It looks like it drops below 75% in the test suite. We can also compare our model directly with the heuristic. A caveat here is that these results are on a subset of the test suite because we wanted to directly compare the heuristic to MLCB. And to do that, we took a subset of the test suite where we had this one-to-one comparison. So we also see a drop here in how the heuristic does in comparison with MLCB. Our hunch was that we're having these drops with the CNN and the heuristic because they're not as robust over time. And actually, if we dig into this result a little more, we're able to figure out why there's this type of drop. So the culprit is really this image shown on the bottom. This comes from a paper illustrating how you could improve upon the canvas fingerprinting technique if you drew this particular type of image. Although this type of image is very rare in our original scrape data, it could be commonly found among our test suite data. And these fingerprints do not generally fit the rules of the heuristic, and they're odd looking enough for our image classifier to think that they're not fingerprinting. So we find that the heuristic and the CNN, the convolutional neural network trained on images, are performing more poorly when they consider these type of images. Lastly, we should note that the obfuscation used in the adversarial perspective is quite heavy. So it makes good sense why the models drop in performance when we look at this. Here's an example. This is one from the paper. So this program draws the image at the top of the screen, and this program looks very similar to the program the LensCrafters was using that I showed in the beginning. When we run this through the JavaScript obfuscator tool, the output looks like this. And in fact, this is then run through the JSNice tool, which was supposed to give us some more natural language understanding to it. And even with that done, it still is very difficult to parse what's going on here. That said, what we found when we looked into this result was that we're actually showing very high recall and low precision. So when our classifiers see this type of data, they're more likely to call it a fingerprinting program. Now the implication of this is that our classifiers in some ways are disincentivizing the use of obfuscation, because when you use obfuscation, our classifiers are more likely to block your program. And that may be a good thing from a policy perspective. So in summary, canvas fingerprinting is a technique that's on the rise. That said, what we've learned is that wholesale canvas blocking would disproportionately block a number of benevolent canvas actions. MLCB improves the state of the art by using images to easily label hundreds of programs. It also provides more robust classifiers given its reliance on text-based data. And it works well despite drift and despite some amount of obfuscation. Finally, we'd like to note that our entire dataset of canvas images and program text is available at the links above, along with the source code we use to build all of our machine learning models. Thanks again for having us at PETS 2021.